Hi, my name is Pooya Jannaty. I am an R&D engineer in the Silicon Engineering Group at Synopsys. In the Silicon Engineering Group, we develop all sorts of technology computer-aided design or TCAD tools to simulate the physics of electronic devices at various levels of complexity. Synopsys was recently awarded a 5-year grant by IARPA to develop industry-ready electronic design automation tools to enable simulation and design of superconducting electronic devices. This program is called SuperTools, and the following presentation is a repeat of what I presented during our first technical exchange meeting with IARPA and our collaborators on our preliminary TCAD endeavors as part of the larger Synopsys team. We would like to gratefully acknowledge the support of the Office of the DNI, IARPA, and the ARO, as well as all the folks from the SCE community who are providing us helpful guidance and advice to make this project a success. We gratefully appreciate the outstanding collaboration we are having with our project partners, including Hypris, WRCAD, Yokohama, Stony Brook, and the University of Rochester, as well as all the feedback and insights from our interactions with ColdFlex and TNE teams. Superconducting electronics holds a niche potential in advancing the electronics industry, such as circuits that can operate at sub-terahertz frequencies to power consumptions and voltage levels that are orders of magnitude smaller than those in the CMOS technology. I will start by briefly explaining what TCAD is and is not. Then, I will motivate my talk by looking at a building block of superconducting electronics, a Josephson junction. I will then go over basic theories of conventional superconductivity and consider their pros and cons for TCAD simulation, and then we'll conclude my talk. What is TCAD? Well, per the Wikipedia definition, TCAD is short for Computer-Aided Design, a branch of electronic design automation that focuses on physics-based simulation of semiconductor device fabrication and operation. As you can tell, this definition does not cover superconducting electronics. Therefore, it is certainly our goal to contribute augmenting this definition by the end of the SuperTools program. Often TCAD is mistook with SPICE simulation. TCAD is not SPICE. SPICE usually makes use of analytical and formulaic ansatz to describe the high-level behavior of a circuit element and is good for simulating relatively large circuits comprised of thousands of transistors, whereas TCAD focuses on one or two devices at a time, but simulates them at great detail. Because of this, TCAD simulations are comparatively much slower than SPICE simulations and need much more computational power to carry out. As I mentioned, one of the strengths of TCAD is first principle simulation of physical phenomena down at the microscopic, or nowadays really nanoscale level. This gives TCAD its predictive power that can even be exploited to predict certain device behavior before it's even manufactured or tested. TCAD is also used as a learning tool by device designers and physicists to understand the intricate phenomena that happen at the microscopic level. This is crucial in today's technology, where electronic devices are so complex that no single formula or trend can describe their behavior. Using TCAD tools, device designers can research the effect of various design parameters and experiment with new forms of devices and materials to find the most efficient path toward the next technology generation. Okay, having briefly seen what TCAD is, let's take a look at the building block of superconducting electronics, Josephson junction. A Josephson junction, in its simplest form, is two superconductors separated by an intermediate layer. This intermediate layer, often called a weak link, can be an insulator, a normal metal, or even another layer of superconducting material. What is amazing about superconductors is that their quantum state can, at a high level, be described by a single wave function, or order parameter, despite being macroscopic in size. In fact, superconductors are closest to what we can call macroscopic embodiment of quantum objects. Richard Feynman, in his famous lectures on physics, has a nice description of a Josephson junction. He assumes that each order parameter on each superconductor on the two sides of the insulator layer satisfy their own Schrödinger equation, but are also weakly coupled to one another, signified by the coupling factor K. He then writes each order parameter as a complex number with an amplitude and a phase and substitutes back to the coupled Schrödinger equations. Upon matching the real and imaginary parts of both sides of these equations, he arrives at the first and second Josephson equations. The first Josephson equation defines current as the time rate of change of the probability of order parameter on one side and relates it to the sign of the phase difference across the junction. This is a remarkable result. We can already see that the phase of an order parameter has become manifest at the macroscopic level. The second equation relates the time rate of change of this phase difference to the voltage across the junction. So you see that applying basic quantum mechanics can immediately give you a qualitative description of a Josephson junction, but this lacks quantitative description and finer details. Now let's take a survey of a few theories of superconductivity and consider their pros and cons with regard to TCAT simulation of superconducting electronic devices. One of the earliest theories of superconductivity was formed by two German physicist brothers, Fritz and Heinz London. They came up with their theory back in 1935. To put things in perspective, this is 20 years after Einstein's general theory of relativity. The London equations can be derived from classical electrodynamics. The first equation relates the time rate of change of the current density in a superconductor to the electric field and the gradient of the same current squared. The parameters you see in this equation are all for a pair of electrons, which we will later see are responsible for the transport mechanism. The first London equation is equivalent to the Lorentz force in electrodynamics, combined with Newton's law, which relate the time rate of change of a carrier velocity or its acceleration to the overall electric and magnetic force exerted on it. If one assumes that the magnetic field is much less than the electric field, the first equation can even be further simplified. The second equation expresses an equation for the magnetic field density H and defines an important parameter lambda sub L, which is called the London penetration depth. This parameter signifies the characteristic distance over which the magnetic field can penetrate the bulk of a superconductor, as we will see below. This second London equation comes from one of the Maxwell's equations, curl of H equals the current density plus the time rate of change in the electric field. We can simplify this equation for a time-independent field so that the Laplacian of the H field is proportional to itself. This will give an exponentially decaying solution of the field going into the superconductor and forms the basis of the so-called Meissner effect, which says that superconductors exhibit perfect diamagnetism. Okay, having gone over a brief description of London equations, let's take a look at their pros and cons from the TCAT perspective. Arguably, the main attraction of the London theory is its simplicity. It captures one of the hallmarks of superconductivity, the Meissner effect, and it only receives a single parameter, the London penetration depth, which again speaks to its overall simplicity. In terms of numerical complexity, it is at the same level as the Maxwell equations, which is not bad at all. In addition, all the equations are linear, so they have good convergence prospects. However, because this theory is based on classical physics, it has no treatment of secondary effects of the quantum phenomena, and it is only valid in homogeneous materials. This last part means that it also cannot handle intermediate states, where different regions of the same material can be in different states of superconductivity. Moreover, this theory is a local theory, meaning that it cannot account for non-local effects. Because of this, its regime of validity is limited to coherence lengths much smaller than that of the penetration depth. This condition does not happen in pure superconductors, therefore London equations cannot be applied to them. Also, in order to have small coherence lengths, the temperature must be high enough to induce scatterings to shorten the coherence lengths, which limits the validity of the theory to temperatures just below the critical temperature of a superconductor. Now let's take a look at a more advanced theory called the Ginzburg-Landau theory that can work on inhomogeneous materials and structures. Ginzburg and Landau were two Russian physicists who came up with their phenomenological theory back in 1950. But because their theory had no underlying microscopic basis, it was mostly overlooked in the West. However, some 9 years later, Garkov proved their theory as a limiting case of the underlying microscopic theory. Nowadays, the Ginzburg-Landau theory is hailed as masterstroke of physical intuition. The Ginzburg-Landau theory solves for a complex order parameter as a function of space. It has many resemblances to the Schrödinger equation, in that you see the conventional kinetic operator acting on the order parameter, as well as the linear term alpha times psi. However, here alpha is not the eigenenergy, rather a fixed parameter. There is also a nonlinear term in psi that can be viewed as the potential term in the Schrödinger equation. The current density is given by the usual formula in quantum mechanics, which comes from the conservation of the probability flow, which has a very nice intuitive meaning as it can be cast into the carrier density times carrier velocity. Alpha and beta are two phenomenological parameters that depend on the critical field and the effective penetration depth, which are both temperature dependent. If you notice, beta is always positive, which means that the nonlinear self-potential term in the original equation is repulsive. Intuitively, this nonlinear term will try to make the order parameter as uniform across the space as possible. You can see the solution of the Ginzburg-Landau in the vicinity of a vortex state. Vortices appear in superconductors when a single magnetic flux line is crossing a superconductor. As you can see, the order parameter vanishes around the flux line, which means that the material loses its superconductor nature at a local level. The magnitude of the order parameter quantifies the state of superconductivity, and therefore can describe inhomogeneous situations. Looking at the figure, you can also see that the B field is only local to the vortex region and quickly dies off, which is again a manifestation of the Meissner effect. Now let's revisit the Josephson junction and apply the Ginzburg-Landau to a simplified one-dimensional junction. After writing the 1D version of the equation and normalizing it, we will further simplify the equation by neglecting the second and third terms for a thin insulator. This allows us to write the order parameter as a sum of two solutions. The solution in red describes the spread of the order parameter from the superconductor on the left, held at a fixed phase of 0. And likewise, the blue solution describes the spread of the order parameter from the superconductor on the right, held at a finite phase of delta phi. If we substitute the solution into the current equation, we revive the first Josephson relation for the current. Had we not ignored the smaller terms, we would have arrived at the deviation of the Josephson relation from the sinusoidal dependence on phase difference. You can see that the Ginzburg-Landau theory provides a more rigorous derivation of the Josephson relations and even can make it more accurate. Let's recap what we have learned about the Ginzburg-Landau theory and consider its pros and cons for TCAD applications. The main strength of the theory is that it can treat spatial inhomogeneity, which could either mean varying superconducting carrier density or mixed states, as well as structures comprised of different materials. This theory is also capable of including fields into the formulation via the vector potential. It receives two parameters, compared to a single parameter in the London theory, which means that it's more general than London equations. And even though more complicated than London equations, it is still by far more tractable compared to the microscopic theories. However, the rigorous derivation of the theory from the microscopic theories shows that the theory is only valid at temperatures near the critical temperature and produces wrong results near 0 Kelvin. The nonlinear nature of the differential equation necessitates use of iteration in arriving at a solution, which means more computation. Moreover, the same nonlinearity means achieving numerical convergence might not always be so easy. From a physics standpoint, because the theory describes a superconductor with a single order parameter, it does not account for secondary effects such as excitations and quasiparticle tunneling. Okay, now let's take a look at the most famous, also the first microscopic theory of superconductivity, the BCS theory. The microscopic theory of superconductivity eluded physicists for decades, but it was eventually developed by three Nobel laureates, John Bardeen, Leon Cooper, and John Schrieffer in 1957, about 7 years after the Ginzburg-Landau theory. The basic premise of the BCS theory is formation of Cooper pairs, which are two electrons bound to one another through an attractive force. The BCS theory successfully explains conventional superconductivity by demonstrating that the Fermi sea of electrons in a normal metal is unstable against the formation of such Cooper pairs. Quantum mechanically, this means that the ground state of a normal metal is no longer a true ground state, below the critical temperature, and its energy can be further reduced through formation of Cooper pairs. The attractive force before a pair of electrons has its roots in phonon-mediated interactions. Here you see two Feynman diagrams for each interaction, where a retarded propagator is shown on the left and an advanced propagator is shown on the right, both from the point of view of the incoming particle K. You can see that in the left figure, particle K emits a phonon that is later captured by another particle with opposite momentum minus K. On the right, a phonon is emitted by particle K in the future and is received by particle minus K in the past. Now let's see what the superconductivity ground state looks like. Let's start by pairing up electrons with opposite momentum and spin from stationary spin-zero Cooper pairs. Mathematically, this can be done by applying pairs of creation operators on the vacuum state. However, as you can see, this is extremely cumbersome and conveys little physics. The genius idea by BCS was to take the occupancy of each pair to depend solely on the average occupancy of other pairs. This is a form of a mean field theory approach in physics. The ground state in the BCS theory therefore takes the form of product of states where there is a certain chance for a particle pair to have been formed, denoted by the probability amplitude V sub k, and its complement, the probability that it has not been formed, U sub k. Of course, U and V need to be normalized to unity for the probability to make sense. The first thing we notice is that with this BCS ground state, we have lost particle number definiteness. We can see this more clearly if we expand the product to express the ground state as a superposition of states with different number of particles. However, this is no cause for concern, as simple number crunching shows that the particle number distribution is very sharply peaked around the average value. As a matter of fact, the more macroscopic the system, the smaller the relative particle number fluctuation. Okay, so far so good. Now all that is left is to determine the form of U sub k and V sub k, which is what we will do next. In order to determine U and V coefficients, we will need to substitute the BCS ground state into the effective Hamiltonian for a homogeneous superconductor. The Hamiltonian comprises the usual single particle contribution, just like in a normal metal, expressed in the first sum. The second sum denotes the interaction between different Cooper pairs. You can see that, for example, pair L can interact with pair K via the interaction term V sub KL. Finally, the last sum is the usual chemical potential. Now all that's left is to use the variational approach in quantum mechanics to minimize the energy of the BCS ground state with respect to the U and V coefficients. Having done this, we can see that the occupation probability of the pair K is unity at energies well below the chemical potential and 0 at energies higher than the chemical potential, and smoothly transitions between the two. We also notice that superconducting pair occupation probability at 0 temperature has a startling resemblance to the Fermi-Dirac distribution at a finite temperature. You can also notice that in expressing V sub k and U sub k, I have defined two quantities, Xi sub k and E sub k. Xi sub k is the energy of a single particle in a normal metal with respect to the chemical potential, and increases monotonically with the momentum number, and E sub k is the corresponding energy for a particle in a superconductor, with the difference that now an energy gap has formed in the superconductor case. I will talk a bit more about the energy dispersion in a superconductor, but before doing that, I would like to give some physical intuition as to the nature of this energy gap and tie it to a couple of interesting notions. Let's start by looking at the term F sub L that is used in the definition of the gap. F sub L is called the condensation amplitude and is an extremely important quantity in the BCS theory. You can see that mathematically it sandwiches between the ground states two annihilation operators, annihilating a whole pair K. You might ask, why should this not be 0, as the operation of annihilation operators on the right ket state must produce a state that is orthogonal to the ground state. To answer that, recall that the BCS ground state has no definite particle number, and that in fact it is a superposition of states with different number of particles. Therefore, when we annihilate two particles from the ket state, the resulting state will still have non-zero projection on the ground state. Okay, but what about the physical meaning of the condensation amplitude? Well, F sub k signifies the average probability that a Cooper pair exists in the ground state. That is, two electrons k and minus k have condensed into a Cooper pair. Now, armed with this notion, looking at delta sub k, we see that it is equal to the sum of scattering from all pairs L into the pair k times the probability that pair L has formed in the first place. Therefore, delta sub k indicates how strongly bound the pair k is, and the stronger the pair, the larger the energy that is needed to break it apart. You also notice that in the alternative expression of the gap, there is an inverse exponential dependence on the interaction term minus v. This is a very odd form, in that it eludes a perturbative expansion based on v, no matter how small v is. This is one of the reasons why a microscopic theory of superconductivity took such a long time to be developed. The pair binding was an inherently non-perturbative phenomenon, which prevented physicists to use the usual perturbative techniques. I promised to say a bit more about the energy dispersion in a superconductor. The energy dispersion plot that I showed you earlier is part of a bigger, yet more familiar picture. On the left, you see the familiar quadratic energy versus momentum dispersion for particles in a normal metal, plotted in dashed line. Much like in a semiconductor, we can adopt the convention to only consider the excited carriers, that is, electrons above the chemical potential and holes below it. However, having adopted that convention, we now need to reflect the bottom part of the dispersion curve over the chemical potential line so that the whole energy is measured upward, just like electron energy. Within this convention, the energy dispersion of a normal metal looks like a wedge above the chemical potential, and when we cool it down to cold enough temperatures, this wedge turns into the red curve and an energy gap above the chemical potential is formed. This red curve describes the energy dispersion for the excited states over the BCS ground state. To see how, let's go back to the Hamiltonian and diagonalize it. We can do that using the so-called Bogoliubov-Valentin transformation, which defines two new creation and annihilation operators, gamma dagger and gamma, as a linear combination of normal operators, making use of the u and v coherence coefficients. The diagonalized Hamiltonian is made up of the ground state energy and the contributions from the excited states. I would like to briefly discuss the density of states in a superconductor before we look at how to use the BCS theory. In the figure below, the density of states in a superconductor is plotted in red and contrasted to the normalized density of states in a normal metal drawn in blue. As evident from the figure, there are no states in the forbidden energy gap, as it should be. However, to compensate for that, the density of states has formed a singularity right above the energy gap. This singularity could pose a source for numerical instability for TCAD simulation purposes and must be dealt with. Armed with the BCS theory, we can now look at various tunneling phenomena by looking at different material structures. Let's start by looking at a normal metal superconductor structure. The tunneling part of the Hamiltonian can be expressed in terms of annihilating a particle from metal A and creating a particle in superconductor B and its Hermitian conjugate. One thing we need to do is express the particle operators in a superconductor in terms of the gamma operators that we defined earlier. Having done this, we can express the current based on the tunneling probability, the density of states, and the Fermi distribution on each side. Looking at the figure on the left, we can see that in order for a tunneling to occur at zero temperature, a bias equal to the superconductor gap needs to be applied to either of the sides in order for the current to start flowing, as there are no states available in the energy gap. The zero temperature IV curve is plotted in solid red on the right. This curve asymptotically converges to the normal metal IV curve in blue at high voltages. The situation is slightly different at finite temperatures. We can see that there is a non-zero current even within the energy gap, plotted in dotted red, which is due to the contribution of the Bogoliubov excited particles, also called bogolons. As another example, we can also analyze tunneling between two superconductors. Here, the zero temperature current only starts flowing when a voltage bias larger than the sum of energy gaps of both superconductors are applied. The discontinuity in the zero temperature current at the onset of current flow is a direct manifestation of the singularity in the density of states. Similar to the normal metal superconductor case, we see the secondary effect in dotted line due to the excited particle contribution at finite temperatures. Okay, we took a rather deep dive into the BCS theory and saw it in action. Now let's analyze its strengths and weaknesses. Unlike the Ginzburg-Landau theory or the London equations, the BCS theory is valid in all temperatures, down to 0 Kelvin. As a matter of fact, it can be used to analyze temperature-dependent characteristics of superconductors and their thermodynamics. Moreover, the BCS theory introduces excitations and paints a picture for particle tunneling, among other things. It also has a larger set of parameters such as the energy dispersion and density of states. But perhaps the main drawback of the BCS theory is its inability to address inhomogeneity. For example, in the case of the position-dependent energy gap parameter. This is also the reason why we needed to study tunneling between materials in an ad hoc way, assuming that the tunneling matrix is already provided to us. Moreover, including external fields in the theory is quite cumbersome. In terms of numerical complexity, it is by far the most demanding of the theories we have considered so far, mainly due to the added dimension of energy for particle enumeration. Some of these drawbacks, especially the inability of the BCS theory to treat inhomogeneity, are serious. Let's look at other candidate theories that can resolve some of the limitations of the BCS theory. One such candidate is the Bogoliubov-de Gennes theory, which is a generalization of the BCS theory. It is even valid when there is a spatial variation in the material composition, potential, energy gap, or even in the presence of scattering centers. The basic premise of the theory is that in these situations, momentum is no longer a good quantum number, and one needs to use the quantum field operators in the position representation. These field operators make use of the Bogoliubov-Vallotton transformation, where now the U and V coherence coefficients are position dependent. Of course, the field operators are defined in such a way to satisfy their own commutation relations. The effective Hamiltonian in this theory resembles the simpler BCS Hamiltonian that we saw earlier, except that the 4 operator interaction terms have been replaced with 2 operators corresponding to a single pair times the average of all other pairs, denoted by the position-dependent delta. Again, you see the signature of the mean field theory, where the many-body interactions are replaced by interactions between the single pair and the average of the rest of the system. However, because this delta parameter depends implicitly on the field operators, we need to use iterative techniques to solve for delta and the fields self-consistently. After diagonalizing the effective Hamiltonian, we arrive at a set of coupled partial differential equations for u and v as a function of space. It is interesting to note that setting delta equal to 0 recovers the ordinary Schrödinger equation for the normal metal. Now that we have set up the basic theory, let's look at the simplest non-trivial example, uniform current in a pure superconductor. In this case, the phase of the gap parameter will be position dependent, and the u and v functions will describe an electron and a hole bound to form a Cooper pair, with the difference that they now carry a non-zero center of mass. Note that we are no longer pairing time-reversed particles, like in the BCS theory. In fact, the BCS theory is of no use here, as the Cooper pairs in that theory cannot carry current. Moreover, if you look at the energy of the pairs, you discover that they are skewed proportionally to the supercurrent velocity. This also means that the delta parameter is no longer the same as the energy gap. As another example to showcase the power of the Bogoliubov-de Gennes theory, let's look at what happens when a normal metal superconductor boundary is impinged by an incoming electron from the normal metal side. This electron, which is shown in blue, cannot enter the superconductor in isolation and needs to enter as a pair. To form such a pair, you can imagine to add and subtract an impinging hole, where the electron pairs up with the added hole and enters the superconductor, and an extra hole is reflected back into the metal. which is shown in green. This phenomenon is called Andreev reflection and is the basis for metal superconductor transport. You can further imagine that if there was a second superconductor to the left of the metal, which is not shown here, the reflected hole could do something similar, which results in another electron being reflected off that superconductor, and this process could happen multiple times as a chain of events. This would give rise to bound states in the intermediate layer called Andreev states. To sum up, we saw that the Bogoliubov-de Gennes theory generalizes the BCS theory very elegantly and can handle spatial inhomogeneity as well as excitations and quasi-particle tunneling in a much more direct way. The only drawback is that of numerical complexity. Not only are parameters and fields position dependent now, but there's an extra layer of computation that is needed to achieve self-consistency. Moreover, the solution size is now doubled, as we need to solve for particle and antiparticle states separately. The final method I would like to briefly mention is the Keldysh non-equilibrium formalism. This is a fully quantum mechanical framework that extends the equilibrium quantum field theory to the non-equilibrium case. The basic constructs in this theory are various flavors of the Green's function, which are very similar to particle propagators, yet are richer than them. This provides a very powerful and general approach to solving the Bogoliubov-de Gennes equations of superconductivity that is capable of treating coherent and non-coherent transport in a non-equilibrium setting. Of course, with everything great, it comes with its downsides, one of which is that it's extremely computationally demanding. It also involves some complex physics and math. In conclusion, I discussed that the EDA tools for superconductivity are lacking, and that the SuperTools program is aiming to address this issue to enable proliferation of superconducting electronic devices. In particular, there are virtually no TCAD tools available in the industry. I also reviewed some of the prominent theories of superconductivity from basic to advanced and argued that because of the quantum nature of superconductors, they are inherently non-intuitive. I also gave the pros and cons for each theory from the TCAD implementation perspective, with an emphasis on the numerical complexity. Slow computation is a computational scientist's bane of existence. The more physical mechanisms one would like to capture, the more sophisticated the model must be, which leads to slower computation time. Therefore, we need to be creative and strike a balance between accuracy, model sophistication, and speed. This is Pooya Jannaty from Synopsys. Thank you for watching.